Hello boys and girls, in this video we are going to proceed to 2.3 capacitor with dielectric. Capacitor might come in different size and shape. Anyhow, for our discussion, we are going to focus on parallel plate capacitor. Parallel plate capacitor is the simplest form of capacitors. It can be constructed by using two identical conducting or metal plates, each having a surface area A separated by a distance D parallel to each other, with no material between the plates. So, in between the plate is a A gap, or we call it a free space. So, for this kind of A-field parallel plate capacitors, the capacitance is given by C naught equal to epsilon naught A over D. Epsilon naught is referred to the permittivity of free space, whereby the value is given by 8.85 to the power of negative 12 farad per meter. A is referred to the area of the plates in SI unit meter squared. D is referred to the plate separation or the distance between the two plates and measured in SI unit meter. We might also insert insulator in between the two plates. When we insert insulator in between the two plates, we call this one as parallel plate capacitor with dielectric. So we might insert dielectric in between the two plates of the parallel plate capacitors. So what actually is dielectrics? Dielectric is an insulating or non-conducting material, for example rubber, plastic, wax paper. So, when dielectric is inserted and completely fill the regions between the plates of the capacitors, it will increase the capacitance by a factor of epsilon R, whereby the capacitance will increase or equal to epsilon R multiplied C naught. For example, I have an A-field capacitor. The capacitance is 3 microfarad. So what happens when I put in dielectric? So if I insert dielectric between the plates, whereby the epsilon R is 4.5, then I'll find out that after I insert the dielectric, the value of capacitance will increase 4.5 times. So I'm going to have 4.5 times 3, a new capacitance of 13.5 microfarad. So by placing a dielectric between the gap, the capacitance will increase by a factor of epsilon R. Epsilon R is called the dielectric constant, or we call it as relative permittivity. So, for parallel plate capacitor with dielectric, the capacitance is given by epsilon R multiplied C naught, whereby C naught is the capacitance for an A-field capacitor. And we know that C naught is epsilon naught A over D. So when we put in, we might also have the capacitance with dielectric is given by epsilon naught epsilon R A over D. Epsilon naught is referred to the permittivity of free space. Epsilon R is what we call dielectric constant. A is the area of the plate. D is the plate separations. C naught will be the capacitance of an A-field capacitors. So boys and girls, when we refer to the formula of capacitance for a parallel plate capacitor, epsilon naught epsilon R A over D, we will find out that the capacitance C for a parallel plate capacitor is directly proportional to the area of its plates, whereby if we increase the area, the capacitance will increase. Second, the capacitance is inversely proportional to the slit the plate separation D, whereby when we increase the separations, the capacitance will decrease. Third, the value of capacitance also depends on the type of dielectric we insert between the two plates, whereby the capacitance depends on the dielectric constant epsilon R. All these relations can be shown clearly through the simulation below. So, class, for example, this one, I have a parallel plate capacitors where starting this is the value of capacitance. With the separations 0.mm, the plate area is 100 mm squared. So if I increase the separation, observe what are going to happen to the value of capacitance and the charge that we're able to store on the plates of the capacitors. So as the separation increase, we will find out that the value of capacitance will decrease and the charge that we can store on the capacitors will decrease. And then what happens if I increase the plate area? So as I increase the plate area, we will find out that as the area getting larger, there will be more charges can be stored on the plates and the value of capacitance increase. Okay. Now let us see how the value of capacitance vary when we insert a dielectric in between the gap of two parallel plates. So let's say I have a dielectric with value of dielectric constant is 2. As I insert the dielectric in between the plates, you will find out that the value of capacitance will increase. There will be more charges that we can store in the capacitors. Okay, when I put it out, then you will notice that the value of capacitance will decrease. So different type of material also might have different value of dielectric constant. Let's say I change it to paper. Paper have a value of dielectric constant 3.5. So let us observe what happened to the value of capacitance. So when I put in, yes, the value of capacitance increase and there will be more charges that we're able to store on the plates of the capacitors. So remember, the value of capacitance for parallel plate capacitors depends on the area, the plate separations, and also the dielectric that we insert between the two plates. So how we define dielectric constant epsilon R? Dielectric constant epsilon R is the ratio of permittivity of dielectric material epsilon over the permittivity of free space epsilon naught. We might also define dielectric constant with the value of capacitance, whereby dielectric constant is the ratio of the capacitance with dielectrics over the capacitance of an A-field capacitors. Or we might also define dielectric constant as the ratio of V0 over V. V refers to the voltage across the capacitor with dielectric. V0 refers to the voltage across an A-field capacitor. Or we might also define dielectric constant by relate it with the electric field strength between the plates, whereby E is referred to the electric field strength for a capacitor with dielectric. E0 is the electric field strength of an A-field capacitors. So dielectric constant epsilon R is dimensionless, do not have any units, and the value is greater than 1. Different insulating material, they might have different value of epsilon R, dielectric constant. For example, vacuum or free space, the value of dielectric constant is 1. Paper 3.7, water is 80.4. So class, now let us zoom in and see clearly how Actually, the dielectric might increase the capacitance. So, we consider a A-filled capacitor. So, initially, the plates are separate by vacuum. Okay, is free space A, and connect to a battery, giving the charge on the plate is positive Q and negative Q. After that, we remove the battery. So when we remove the battery, the capacitor become an isolated system. There will be no path for the charge to flow out from the capacitors. So the charge on the plates will remain constant. So there is an electric field built up between the plates of the capacitors. So I denote it as E0. And recall from the concept we learned in topic 1, electric field line always run from positive towards negative. Okay, so after that, we insert dielectrics into the space between the two plates. What are going to happen? So as we insert the dielectric between the plates, we will find out that the molecule of the dielectric, they will start to align themselves, whereby their positive end will pointing towards the negative terminal of the plates, and their negative end will pointing towards the positive charge plates, So this will create a reverse electric field. Okay, so the alignment of the dielectric molecule, so you see this one, the alignment of the dielectric molecule will create a reverse electric field, which is opposite to the electric field of the capacitor. Okay, so the electric field created by the dielectric I denote as E subscript D. The electric field of the capacitor I denote as E0. So this electric field E0 now will be partially cancelled because they are point in opposite directions. So the net electric field strength of the capacitor now will be reduced. Why? Because as you recall the concept, electric field is vector quantity. So the electric field created by the dielectric is pointing to the left. The electric field of the capacitor is pointing to the right. So E0 minus ED. So the net electric field strength will become lesser lah. Dia akan jadi kurang lah, reduce. So from the equation E equal to V over D, recall this is the electric field formula we use for parallel plate or uniform electric field in topic 1. So we find out that as the electric field for the capacitors decrease, the voltage will decrease because E and V is directly proportional. And then recall from the formula of capacitance, C equal to Q over V. Since the charge in the capacitor is constant, so the capacitance is inversely proportional to the voltage. So as the voltage across the capacitor decrease, the capacitance of the capacitor will increase. So this is how the dielectric, when inserted into the capacitor, it might increase the capacitance. Okay, so clear? So class, before I end the videos for this subtopic, I would like to remind you on one thing. When we do the modifications for capacitor, we must always ask ourselves, is the capacitor connected to a battery or not? Okay, like what we have done with the explanation on the effect of dielectrics on the parallel plate capacitors, we disconnect the battery from the capacitor. So when we disconnect the battery from the capacitor, the charge is constant. Anyhow, sometimes we might do the modifications of the capacitors. For example, we insert the dielectric with battery still connected. So if battery is still connected, then the charge will free to flow from the battery to the capacitor. So at these particular situations, when our battery is still connected to the capacitor, then we shouldn't treat our charge is constant, but then the voltage across the capacitor is always remain constant. So be careful. So be careful. You have to ask yourself which quantity is constant by referring whether the battery is still connected or the battery is already disconnected. Okay, for example, this one, I might also insert a dielectric at constant voltage. Constant voltage means I still connect my capacitor to a battery. So for this case, since I still connected to a battery, the voltage V will always remain constant for these charged capacitors. So C must increase when I insert the dielectric. We understood as long as we put in dielectric, the capacitance of the capacitor will increase. So as the dielectric is inserted, it means that our capacitance increase. So more charges will be pulled from the battery and dissipated on the plates of the capacitor as its capacitance increases. So from Q equal to CV, if our voltage is remain constant because we still connected to battery, C increases, so we know that our charge must also increase. Okay, so this is the situation whereby we do the modification. We insert the dielectric with capacitor still connected to battery. So when capacitor still connected to battery, we have to bear in mind what is constant? Our voltage stay constant. Okay, our voltage stay constant. So we have come to the end of the video for subtopic 2.3, whereby we already discussed about how we calculate the capacitance for a parallel plate capacitors, and from the equation we know that the capacitance for a parallel plate capacitor depends on the area, the separation between the plates, and also the dielectric that we might put in between the charged plates of the capacitors. Then we have already zoomed in and see how the dielectric increase the capacitance. So with this, you might try to attempt tutorial 2, question 8, 11 to 15, and I shall meet you in tutorial class to discuss on the questions. Okay, then with this I end my videos. Thanks for your focus and attentions throughout the videos, and we shall meet you again on the next topic, direct current and direct current circuit. Thank you, class.